Alright, so what we're going to look at in this video is trying to understand shear stress in beams, and specifically for a given cross-section, what the shear stress distribution is on that. And I've got this entitled, Shear Stress in Beams, an intuitive approach, because we're going to start to investigate, what this distribution of shear stress is, but I'm not going to use any numbers. I just want to use some free body diagrams and some really basic equilibrium to try and help provide sort of an intuitive sense on why our shear stress is distributed in the way that it is. And so hopefully that will provide a mental model, which will mean that when we eventually go and we look at deriving what the shear stress is using mathematics, that we can keep some of those rules and some of those relationships as to why we see the shear stress distributed in the way that it is, kind of in our heads, and so that we'll be less likely just to get lost in the math and instead be able to utilize this sort of mental model. So how we're going to do that is I've drawn us a little beam here. So it's just a simply supported beam with a point load in the middle. It's a rectangular cross section, so it has width B and depth D. And then I've gone ahead and drawn the shear force and bending moment diagram. And so this is we've already kind of we've got the tools to deal with it at this stage where we know that there's shear force across the whole beam. We know there's a bending moment across the whole beam. But how are those related? And always a great way to start whenever we're trying to understand a structures problem is to draw a free body diagram. And so we'll do just that. So let's take a free body diagram over on by this support. We'll call that free body diagram 1. And we'll just draw that down here. So FBD 1, and it's got some distance. It's got a shear force pointing down. There's a reaction P over 2 pointing up. And then there is also an internal moment. So there's an M and a V. All right, so that's, again, nothing earth-shattering there, because that's kind of what our shear force and our bending moment diagram are saying, that at some distance, well, there's a shear force, and a bending moment. All right. But if we're interested in shear stress, really what we want to know is how this force acts over this area of cross-section, because that's all our stress is a force acting over an area. Well, we can think about that really by breaking this out into the two different forces. We can look at first our bending, which we've learned how to, what that distribution looks like. And then we can use that to help understand, what our shear force is going to look like in that distribution. So if we just look at the bending component, and all I'm doing is I'm just going to redraw this sort of in 3 dimensions there, just to look at the stress distribution. So we've got some width B. That's our section there. So just the bending component, so just from this moment, we know that our bending stress equals my over I. So our bending stress varies linearly with the depth of the section, and it's going to be dependent upon the second moment of area, or the moment of inertia, I of the section. And so we'll just draw that out. So we know that it's going to, and we've already learned this, it's going to be a maximum at the extreme fibers, and then it will come to to 0 at the neutral axis. Be compression in the top and tension on the bottom. And then I'll just draw, this 3D view I'll just draw that as a profile over here. So our stress, compression on the top, tension on the bottom. All right. Well, so we've already learned that in this class. We know that's our distribution of bending. So that takes care of the M. What about the V? So we know that the stress state here is going to be the superposition of M and V, so the addition of it. So we have a shear component. And that shear component is just going to be, again, we'll just draw out our three-dimensional section here just to help illustrate the point. We know that there will be some shear stress acting down it. What we don't know is the distribution, and so, that distribution, if we draw it out here, so if this is our beam, is that distribution, is it an average, and is it uniform across the whole area? Is it a triangle? Is it come out like bending stress? Does it come out in some shape here? So this is what we're going to look at and find out, well, which of these different profiles does that shear stress occur in? And what we're going to do is, because it has to be in equilibrium with the moment, we can use our knowledge of how the stress is distributed within the moment from bending stress to find out, well, what shear stress is needed to balance that stress out and keep the body and this beam in equilibrium. So that's what we're going to do. So we will start with, again, we will take just the same free body diagram, but all we're going to do is we're going to look at we'll take a second cut. We'll just basically cut it through the top, and we'll just look at this top section here. And we'll do that over different heights coming down, and we can see, well, what's the shear force that's going to occur there. So let's start with that. So if we have, we'll just redraw that free body diagram here. We have our reaction force of P over 2. We have our shear force V, and our bending moment M. And we'll give ourselves a little coordinate system. We'll have Y going up, X going to the right. So what we're going to look at first is we're going to take a slice through here, look at this top section, and we'll just look at a section. We'll have that depth be D over 8, with the total depth is D, as we saw previously. So we're just going to look at the top 1/8 of that section. And so what is that? And we'll call this sort of, free body diagram D over 8. So we know that we have some height here. That height is D over 8. And that we know, so we can look at what our bending stress is over that distance. So we will have a bending stress distribution like that. So it's kind of the top of the triangle here, right? So if our total profile is a linear distribution of bending stress, we're looking at the top 1/8 of it there. And so there will be some, resultant compression force, C, acting here. Well, we know that we also have a shear stress, tau, and we're going to have a shear stress which is acting all along this cut edge. And this is what we saw with our derivation of stress, general stress, is that if we have transverse shear, we have to have longitudinal shear. So we'll just call that tau x. And we know that at the very corner here, that little red corner, the shear that's longitudinal and the shear which is transverse have to equal each other. So tau x has to equal tau y at corner. We'll call that tau y. So that's a good first step. We know that that as we if we take deeper and deeper cuts, well, we know that this force here has to equal this force to keep everything in equilibrium, and so that means that we can slowly plot what our transverse shear is down the depth. So we'll just call this C, we'll call it C1. So we know that if we sum the forces in the x direction, that equals 0. The sum of all of this shear stress of tau x over, we'll call that A, this area, has to equal C1, this resultant force. So we know that this force has to equal this force by definition for equilibrium. All right, well, let's look at another section. So let's look at d over 4 free body diagram. It's going to look fairly similar, but our depth has increased. So again, you've got a compression block here. So you've got a distribution from our bending stress. So remember, this is our our bending stress. And again, there'll be some resultant of this volume of stress acting at the centroid. We'll call that C2. And that's got to get balanced by some longitudinal shear. Again, we'll call that tau x. And there's a transverse shear, tau y. And again, here right at the corner, these two have to equal each other. And so we can go through, we can see some of the forces in the x equals 0 again. We know that sum of tau x times A equals C2. All right, well that's coming along there. Let's do another one. Let's do d over 2. So half the depth over 2. So that's d over 4. Half the depth, d over 2. As you can probably tell from the pattern that we have, we're going to have a longitudinal shear stress, tau x, and then we have our bending stress, and that's going to be, because we're down to d over 2, that's the location of the neutral axis for a rectangle, so we know we have a triangular stress distribution, sigma b, and that resultant, we'll just call that whole thing C, because that's the entire compression block, and that's going to be 1/3 from the corner here acting. And again, we can sum our forces. X equals 0, and then we have the sum of tau x times A equals C. And just like with the other two right here at the corner, these two, the longitudinal shear and the transverse shear, have to equal. So we're starting to see a pattern, and that is because our longitudinal shear, as we progress further and further down the profile, well, the amount of compression stress from bending gets bigger and bigger. So this little block of stress, which is only d over 8, and times the width over the section that's acting, and then just the small area of this. Well, if we go to d over 4, well, C2 is bigger than C1. If we go to d over 2, C is bigger than C2 and C1. And because this longitudinal stress has to equal this compression block, that means that as we're going down the section, we get a bigger and bigger longitudinal stress. So that's kind of one of the neat first things we can see. Well, let's just go a little bit further. Let's go to 3D over 4. Let's go to a depth of 3/4 of the depth and coming down from the top. So again, we're going to have some longitudinal shear because we've opened that up. We've got our transverse shear. We know they're equal at the corner and that little block. And then let's just draw our bending moment distribution. So if this is d over 2, and this is d over 4, so this is the location of our neutral axis, well, then we will have our compression block come down here, and we have a small bit in tension. So we have compression, and we'll call T1 just that small component of tension. So we sum our forces in the x, and that equals 0. So you've got the sum of tau x, and that's tau y. Sum of all of that, tau x over the area, has to equal C minus T1. So this is interesting. This is another interesting thing, because now we have this this tension force which is helping act. That means that after we go past the neutral axis, past the centroid of this section, our shear stress actually starts going down, which means that our, if we know that we come up and then come down, we know that the point where we change, well, that's our location of maximum stress. All right, so we've learned something. So as we go down, we get bigger and bigger because we have a larger and larger compression force that we have to resist with this longitudinal shear force. Once we go past the neutral axis, then we have the tension force, so this longitudinal shear force goes down. We also learned that, from our previous lesson, that at a corner, our longitudinal and our transverse shear have to be equal. So, you need to have tau x and tau y all equal to keep that little block from rotating. Tau y, tau x. So, what this means, well, I think we can take a stab at what our shear stress distribution looks like. So, so taking what we've learned, and again, we haven't used any numbers. This is just to kind of get an intuitive feeling. We know we've got our depth D, and this is our P over 2, some shear, some moment, and I'm just going to go just plot some lines. So this is going to be, that's our D over 2. Then we can plot, D over 4 and D over 8. So our bending stress is just, we've already learned this one. It's just going to vary linearly. And it's going to be 0 at the neutral axis. But then our shear stress, now that we've seen this pattern, well, we know, so we take our shear stress, because we have a larger and larger bending stress to resist until we get to the neutral axis, and then the tension helps us out, and we have a smaller and smaller compression force to resist. We know that we're going to have a maximum shear stress at the neutral axis. So we have tau max. We also know that for our vertical shear, so our transverse shear, it's just going to equal the longitudinal shear at the corner. And so we can just go ahead and kind of plot the relative amount. So we know that, well, when we're at d over 4, this area is pretty similar to this area. So it's going to be a little bit smaller, and that's going to be symmetric. When we get to d over 8, it's a much smaller area here. So d over 8, that's going to start coming back. And then right if we have d equals 0, so basically right at the very edge, well, there's no real compression force there, so we have to come back to 0. So we end up with a shear stress distribution that looks something like that. So and we will find out in the next lesson that it actually goes as a parabola. But you can see just simply from, no numbers, nothing at all, just from free body diagrams and equilibrium, we now have some intuitive sense of how shear stress varies along a rectangular section. And that is, it's got to be, some rules. We know that tau x has to equal tau y, so we learned that in the last lesson on our derivation of general shear. We know that tau equals 0 at a free surface. So free surface is just top or bottom. So basically where there's nothing to shear against, where there's nothing to do this. So, I'm creating a shear force of friction between my hands. Well, I don't have any shear force there if this is a free surface. So that's our sort of second rule. And then our third one, our maximum shear stress is at the neutral axis, and that's because that's our maximum either compression or tension force that we have to resist longitudinally, and because of our transverse shear has to equal our longitudinal shear, that's why we see our profile in this manner. So that's our overview now. So what we're going to look at next is starting to put some numbers to this so that we can have an equation to be able to calculate what these actual points are at any point up the depth of the section. And but yes, I hope this has given you a nice intuitive feeling for shear stress. And let's take that intuitive understanding and sort of these three rules that we have into our derivation, where we're going to get a little bit heavier into the math, use a little bit of calculus, but again, it's all based upon free body diagrams and equilibrium. So with that, this will end the lesson.